Let's work on some examples to reinforce the learning. We have the circuit here. The circuit is a simple circuit, has 3 resistors. The resistor that connects to the terminal A directly is the main branch resistor, and that is 10 ohm. The 2 resistors in 2 parallel branches, R1, R2 equals to 3 ohm and 6 ohm. We want to find the total resistance of this circuit. Again, we know the rule of thumb. Locate the source, find a resistor that is the farthest away from that source, and we start merging from that resistor towards the source, such as R2. As shown in the circuit, R2 is the farthest resistor. So we can start merging R2 towards the terminals AB. R1, R2 connected in parallel, so we start merging them. Rp, the parallel resistance, the total resistance of the parallel branches, equals to R1, and here is the symbol for parallel, 2 vertical lines, R1 parallel to R2. And we know the formula for finding 2 resistors connecting parallel is following: R1 times R2 divided by R1 plus R2. Next, we substitute the values into those variables. We replace those variables by the numbers. R1 is 3 ohm and R2 equals to 6 ohm, divided by R1 plus R2, that is 3 ohm plus 6 ohm. 3 times 6 equals to 18, and for the denominator, 3 plus 6 equals to 9. 18 ohm times ohm divided by 9 ohm. There are 2 ohms units on the numerator, because as you can see, 3 ohms times 6 ohm, that should be 18 ohms. If this causes confusion, I wouldn't worry about that too much, because the number at the end is for resistance, and the unit for resistance is ohm. So 18 over 9, that is 2 ohm. The parallel branch equals to 2 ohm. To make it easy to see what's going on here, perhaps it's easy to replace the parallel region by just one resistor Rp, the 2 ohm, and as shown here. You can see Rp, the 2 ohm resistor, connected in series with the R0, the 10 ohm resistor. And we can find the total resistance now. The total resistance Rt is the sum of both resistors, that is R0 plus Rp. And then next, we just substitute the values into those variables. R0 equals to 10 ohm, and Rp is 2 ohm. Adding them up, the total resistance Rt equals to 12 ohm. So the total resistance of the system equals to 12 ohm. If we put the original circuit back here, that is the same. All the resistors combined equals to 12 ohm. In other words, this system's resistance equals to 12 ohm. Continue from previous circuit, now we're going to add a source here. We add a 12 volt DC source into the circuit. Connect the source between the terminals. The question is, how much current flows out from the source and delivered to the system? We have a special name for this kind of current. It is called the main branch current. As shown here, it is labeled as IT, where T stands for the total current entering to the system. Either we can call it total current or main branch current. So let's put a circuit here, and we can just replace those 3 resistors by that single resistor, R total. From previous example, we know Rt equals to 12 ohm. Now we can apply Ohm's law, because this circuit, the replaced circuit, has only one source and 1 resistor. We can apply Ohm's law to find the total current. RT equals to 12 ohm. We calculated from example 1. And we know Ohm's law current formula is V over R. For this circuit is Vs over RT. Next, we can substitute the numbers into it. Vs equals to 12 volt and RT equals to 12 ohm. The current equals to 1 amp. So here shows the reason why we need to find the total resistance of the circuit. The next step, we can find the current, the main branch current. Once we know current, we can find more things, such as the current in every branch, and the power dissipated on every resistor, the voltage drops on every resistor, perhaps the total power dissipated in the system. Such as example 3, let's find the voltage drops on resistor R0. So put the circuit to the side, and we know IT equals to 1 amp. We calculate this in example 2. Since that 1 amp current passed through R0, we can apply Ohm's law to find the voltage drops on R0. From the Ohm's law voltage formula, the primary formula, we know V equals to I times R. So V0, the voltage drops on R0, equals to the main branch current multiply R0. Substitute the values into those variables. IT is 1 amp, R0 equal to 10 ohm, the product equals to 10, the unit is volt, which is 10 volt. The voltage drops on R0, called V0, equals to 10 volt. The next question can be how much voltage drops on R1 and R2. We know the voltage drops on R1 should equals to the voltage drops on R2 because both resistors connected in parallel. This is the same voltage across nodes C and D. So if we can find out the voltage across node C and node D, we figure out the voltage across R1 and the voltage across R2. We know KVL, the Kirchhoff voltage law. The total voltage in a closed loop equals to 0 volt. Or we have another formula for KVL. The source voltage equals to the sum of all the voltage drops in the closed loop. So we can say VCD, the voltage between node C and D, equals to the total source voltage Vs. Remove the voltage drops on R0. The leftover, the remaining voltage, is the voltage between node C and D. Substitute the values into those variables. Vs equals to 12 volt, V0 equals to 10 volt. So VCD equals to 2 volt. 2 volts left for node C and D. Since we find the voltage between CD, the next example, example 4, we can find a current that goes through R1, called I1, and also the current goes through R2, called I2. Again, the voltage between node C and D is 2 volt, which means voltage across R1 is 2 volt. Voltage across R2 equals to 2 volt. Now we can find the current for every parallel branch. We can simply use the Ohm's law current formula. I equals to V over R. So for I1, that equals to VCD over R1. Plug in the numbers. VCD is 2 volt divided by R1, 3 ohm, which is 2/3 amps. Punch these numbers into a calculator. The number is infinite long, and we just need to keep 2 digits after the decimal point. So I1 is rounded to 0.67 amp. Apply the same Ohm's law formula, the current formula for finding I2. I2 equals to VCD over R2. And then plug in numbers. Is 2 volt over 6 ohm, right? 6 ohm for R2. And the current equals to 1/3 amp. Convert it to decimal and keep 2 digits after the decimal point. The answer is rounded to 0.33 amp. The next question can be how much power dissipated on every resistor. As shown in the note card, power has 3 formulas. There are 3 power formulas. P equals to voltage times current. That's the primary formula, the definition of electric power. And that also equals to current square times R, right? I squared times R equals to V squared over R. We can use any of the 3 formulas, any of them, as long as we know the quantities, the 2 quantities. Here, if you look at every resistor, we know each of their values. We also know the current that goes through every resistor. So for this question, I pick formula 2, the I squared times R. Following information has been calculated already. We know this information. We know the total current. The current goes through R0 equals to 1 amp. I1 equals to 0.66 amps. And I2 equals to 0.33 amps. Now we are ready to find the power dissipated on each resistor, such as the power dissipated on R0. P0 equals to the total current square times R0. Plug in the numbers. 1 amp square times 10 ohm. The unit for the current is amp, no prefix. The unit for that resistance is ohm, no prefix. At the end, the unit for this power is watt with no prefix. So 1 squared times 10 is 10, is 10 watts. Now let's find the voltage drops on resistor R1. This time I pick the first power formula. Power equals to V times I. In this case, the power drops on resistor R1, the P1, equals to the voltage across that R1, which is VCD times R1. Plug in the numbers. We know VCD equals to 2 volt, R1 equals to 3 ohm, the product equals to 6 watts. Now find the power dissipated on R2. We can use the same formula again, but it's the formula for finding R2. That is P2 equals to VCD times R2. Plug in the numbers. VCD is 2 volt, R2 equals to 6 ohm, the product equals to 12 watts. 10 watts drops on R0, 6 watts drops on R1, and the 12 watts drops on R2. Now let's work on this example. In this example, we need to find the total power dissipated on the entire system. From example 5, we know the power drops on every resistor. They are 10 watts for resistor R0, 6 watts for resistor R1, and 12 watts drops on resistor R2. The total power dissipated on the entire system is the sum of all individual powers. In other words, we can simply add the individual powers. It is additive. Plug in the numbers. 10 watts plus 6 watts plus 12 watts. That equals to 28 watts. So the system receives 28 watts. The total power of 28 watts dissipated on the entire system. Or we can say the voltage source provides a total of 28 watts into the system. So the system receives 28 watts.